In this section, we'll take a look at series that have negative terms within them. And the most common type there is called an alternating series. And alternating series, what happens here is the terms in the sequence alternate between positive and negative. And it doesn't have to be necessarily like every other term. It could be like every 2 terms or every 3 terms or whatnot. But in general, the most common type is something that alternates every other term. So, for example, if we look at the series I've listed here, the series from 1 to infinity of -1/2 to the n, as we allow, say, n to equal 1, if I plug that into the sequence, that would be -1/2 to the first power, which is -1/2. All right, and then when n is equal to 2, I'm looking at -1/2 to the second power, so that results in a positive answer. So that becomes positive 1/4. And then when n is equal to 3, we would have -1/2 to the third power, and something to a negative to the third power would result in a negative, and 2 to the third is 8, so this would be -1/8. And then the fourth term would continue in this pattern. So for instance, that would be back to positive, so 1/16. And these terms would continue to alternate forever. All right, so then another example. This one's actually called the alternating harmonic series. I have -1 to the n plus 1. Now to be careful, because the n plus 1 makes a difference, because if I put n equals 1 in, this is going to be -1 to the second power. So the first term is positive, so this would be 1/1, and then when n is 2, this would be -1 to the third, which is negative, over 2, so -1/2. And then when n is equal to 3, then I have -1 to the fourth, which is even, so that becomes +1 over 3, so plus a third, and then it would be minus a fourth, plus a fifth, and continue this pattern forever. And when it comes to testing convergence of alternating series, it turns out that an alternating series has a much better chance at convergence because of the cancellation of negative and positive terms as you're adding up the terms in the infinite sum. So if we compare a few partial sums for a few terms of the harmonic series and the alternate harmonic series. So for instance, if I perhaps calculated the harmonic series, the first 5 terms, so the sum of the first 5 terms, that would be 1 plus a half plus a third plus a fourth plus a fifth. And I'm just going to estimate this in the calculator, so 1 plus 1/2 plus 1/3 plus a fourth plus a fifth. All right, so that's about 2.28. So let's just say that's about 2.28. I just rounded to a couple decimals. Now, the alternating harmonic, if I sum up the first 5 terms, well, it's 1 minus a half plus a third minus a quarter plus a fifth. So what's happening here is I'm going to get some cancellation. Let's see if I can do this faster and just change some signs in this. All right, so 1 minus a half plus a third minus a fourth and then plus 1/5. So the total now is about 0.783, or I'll just say 0.78 for simplicity here. You can see that this is much closer to 0. it's going to converge. It's much more likely to converge than its non-alternating counterpart because of that cancellation. And that's why the alternating series test is actually a little bit easier than most to apply. So the alternating series test says a series of the form, all right, -1 to the n plus 1 times b sub n, or if it's -1 to the n times b sub n. And that's effectively the same. It just kind of changes which term, like if the first term is positive and the second one's negative, or the reverse. All right. One thing I do want to mention here is like b sub n, this right here, b sub n is non-alternating because the alternating piece is the -1 to the n, and that's not included in b sub n here. So we've kind of separated the alternating part of the sequence from the rest, right? And then this piece right here is called our alternating term. So that's what makes the sequence alternate. And it can look different than that. Like, for instance, if you're multiplying by cosine of n times pi, for instance, well, then, that could end up being positive or negative, just depending on what the value of n is for different integer values. So it doesn't have to be -1 to the n. Like, it can look like something else, but this is most commonly what you'll see. All right, so knowing that b sub n is the only thing that's actually being tested, or if you consider that the test is actually the absolute value of the whole sequence, that's fine. Either way is fine. But first off, we need this to be a decreasing sequence. So it says it converges if b sub n plus 1 is less than or equal to b sub n for all n greater than or equal to 1. And actually that doesn't have to be greater than or equal to 1. It can be in general just starting at some point, some finite value along in the sequence. And if it's decreasing from there on, that's fine. All right, so this right here just tells me that the sequence is decreasing. And this b sub n is the non-alternating part. So it's not that the alternating pieces are decreasing, because that doesn't really make sense, because one's increasing, one's decreasing, one's increasing, and it just flip-flops. So you can think of it as the absolute value of the whole thing or just the non-alternating piece, okay? And then the other thing is, so it has to be decreasing, but then the limit of the terms of the sequence have to go to 0. And this is, again, the non-alternating part of that sequence. Oops, I erased too much there. All right, so b sub n is non-alternating, okay? So sometimes you'll see this stated as the limit as n goes to infinity of the absolute value of a sub n. And that's fine too, but as long as you just remember to remove the alternating term, then that's fine, okay? So if you think about this, this actually is the same as the very first test we looked at, which was the divergence test. The divergence test, however, couldn't prove convergence. But here, it actually is proving convergence for alternating series. So if you have an alternating series and the terms are going to 0, it will converge. So that's kind of nice, because the test is really just coming up with the result of an infinite limit. So let's see a few examples with it and find out what we can. All right, so this first example, we want to find out if this series converges or diverges. So it has an alternating term, and the alternating terms are generally very vivid and very easy to see. So once you see that term, it's very much a clue to go for the alternating series test. Now, we'll look at some series tests that will also apply to alternating series, but in general, I think it's most common that if you see this alternating term, just jump right into the alternating series test. All right, because it's pretty straightforward, I generally do the limit first. So we want the limit as n goes to infinity. And like I said, you can think of this as the absolute value of the whole thing. And the cool thing about that is when you take the absolute value of this whole thing, then effectively it just removes the alternating term. Or, since that's always the first step, you can really just start with the absolute value of just the non-alternating counterpart. Now, this limit, pretty straightforward. We have a rational function where the degree in the denominator is larger than the numerator, so that's going to result in 0, and so that holds. All right, that's one thing that is necessary. The other thing is that this has to be a decreasing sequence. So what we need is b sub n plus 1 to be less than or equal to b sub n. All right, so if you're having trouble visualizing that, just think of, what a decreasing sequence would look like. Okay, and we could say this is b sub n plus 1, and this is b sub n. All right, if it's decreasing in value, then b sub n plus 1 is less than, on the y-axis, than b sub n. So that's what it means to be decreasing. So effectively, we just need to plug in and see what happens. So b sub n is the non-alternating part. So it's just this. So b sub n plus 1 would be 1 over n plus 1 quantity squared, and that needs to be less than or equal to 1 over n squared. Since all these terms are positive, we can freely just multiply, cross multiply in this case. N squared is less than or equal to n plus 1 squared, or n squared is less than or equal to n squared plus 2n plus 1. And the rules on these inequalities are still the same in all the problems. Like, you want to get it to the point where it's just completely obvious. Like, you don't need any sort of knowledge of a lot of mathematics in order to determine that this is a true statement. And usually they work out that way. So if I subtract n squared from both sides, then I have 0 is less than or equal to 2n plus 1. And since n is defined on only the positive integers, this is true. So both parts of this alternating series test hold, so this series converges. Okay, and you do need to do both parts. The only time that you don't need to do both parts is if the first part you do fails, and that's going to tell you that it's going to diverge. So let's look at another example. Determine whether this series converges or diverges. So we have the alternating term, and then that's multiplying n over n plus 1. So with the alternating term, I'll jump right into the alternating series test and start with the limit as n goes to infinity, and I'm just going to jump right into the limit of just the non-alternating part, because the first step is just take the absolute value, which takes away the alternating piece. All right, so this is a rational function, but now the degrees are equal. And when the degrees are equal in a rational, you take the ratio of the leading term coefficients. So we get 1, which is not 0, so therefore this is diverging. There's no reason to check to see if this is a decreasing sequence, because once one part of this fails, it doesn't matter. It's going to diverge at that point.